Hello everyone, today we're going to be going over the January 2025 Chemistry Regents exam. In this video, we're going to be focusing on part B1, which are 20 multiple choice questions. A link to this test can be found in the description of this video if you want to follow along at home, and you'll also find videos going over part A, B2, and C of this exam if you want a full review of this test. So check out everything in the description. That being said, we're going to go ahead and start off with number 31, which asks us to approximate the mass of an ion that has 12 protons, 13 neutrons, and 10 electrons. So when you're finding the mass of an ion, you need to remember that the only things that contribute to the mass are the protons and the neutrons. Right? Electrons do not contribute to mass. They are extremely tiny. They have little to no mass. Okay? Protons and neutrons both have a mass of 1 atomic mass unit. So if we have an ion that's made up of 12 protons, well, 12 protons weighing 1 atomic mass unit each is 12 AMUs. And then if we have 13 neutrons, and they're each 1 atomic mass unit in mass, that means that that's 13 AMUs. And if I add 12 plus 13, I get 25, which is going to be my answer. This weighs 25 atomic mass units. Number 32 says, given the bright line spectrum of element X and the spectra of 4 other mixtures, which mixture contains element X? So essentially, when you place element X in this bright line spectra environment, it releases light in these bands only. All right? These are mixtures that contain element X and other elements. And then when you place them in a certain mixture, they're going to also release light. Whichever mixture contains element X is the one that's going to have this same banding pattern in it. All right, this is kind of like a marker that we use to identify element X. So whoever else has these marks in these exact same locations are going to be the mixtures that contain X. So let's look through these, right? Automatically, we can eliminate mixture A, and we could also eliminate mixture C because they don't have this first band that element X has. All we're doing here, guys, is we're just matching up the banding pattern. So element X has this first band here, mixture A doesn't, mixture B does, and mixture D also does. All right, then we look at the next two bands. Here we have a band here. Oh, well, so does mixture B. And here we have another band here, so does mixture B. Guess what? Mixture C doesn't have a band here, so it must not have X. All right, and let's make sure that mixture B is the right answer. Let's look at this line right here. Oh, this line matches up with this line. This line matches up with this line. Mixture B contains this marker, right? It contains these emissions of light, which means that mixture B must contain X, okay? You'll be asking, well, oh, what about these other two lines? Well, these must be the markers for other elements. Again, it's a mixture, so it contains both X and other elements. Number 33 asks us, what is the number of valence electrons in an atom in the ground state with an electron configuration of 2, 8, 18, 3? So this is the innermost electron, right? And this is the outermost group of electrons, okay? So what these are the number of electrons in the different orbitals, right, surrounding the nucleus of this atom. So if this is, let's just say this is atom A, right? We have one shell that contains 2 electrons, then a second shell that contains 8 electrons, then a third shell that contains 18 electrons, and finally, a fourth shell that contains 3 electrons. The valence electrons are found in the outermost shell, which is this one that contains 3 electrons. Another way to think about this is the leftmost number is the electrons in the innermost shell, and the rightmost number is the electrons in the outermost shell, okay? Or to solve this question quickly, just look at the last number. The last number is 3. That means that there's 3 electrons in the last or the valence shell. So that means that any electron in a valence shell is a valence electron. Number 34 asks, which statement describes the general trend in electron negativity and atomic radius as the first 7 elements in period 3 are considered in order of increasing atomic number? All right, so if we look at the periodic table of elements, the atomic number is this bolded number down here. And if we look at the period, remember, periods go left to right. Okay, so if we're looking at period 3, it's this whole line going left to right like this. And in this case, we're increasing in atomic number. So 11, 12, 13, 14, 15, 16. So we're going from left all the way to right. And you should know that as we go from the left side to the right side, the electron negativity increases. Why? Well, these have more protons in their nucleus, meaning that their nucleus is more positively charged, right? What's more positive, a nucleus that contains 11 positively charged protons or a nucleus that contains 18 or 17 positively charged protons? What's the one that contains 17 positively charged protons? It has 6 more units of positive charge. Now, negative and positives are attracted to one another. So the more protons that you have going this way, the higher the attraction you'll have for more electrons because you have a larger positive force in your nucleus to attract them to, right? So as you increase in atomic number, the electron negativity is going to increase, right? Now, think about it this way. If the electron negativity is increasing, if you're attracting electrons with a greater strength, what's going to happen to your atomic radius, right? Let's say that we have an atom of chlorine. Because this chlorine is extremely electronegative because it's almost all the way on the right, it's going to pull in its shells, its electron shells, a much closer to itself than, say, sodium is. Sodium is all the way on the left. It has a low electron negativity. So it has a very weak pull on its electrons. So if I were to draw out the shells, they'll be a lot further spaced out from the sodium because this center is less positively charged and it pulls the electrons less closely to it. Okay, so as you go from left to right across the period, the electron negativity goes up, but the atomic radius goes down. All right, so what's going to say that? Well, that's going to be choice 3 or 4. Electron negativity increases and atomic radius decreases. Choice 3. Number 35 asks us for the chemical name for KClO2. So whenever you're naming something, first of all, look at the metal and then look at the non-metal. Okay, so let's split this up in half. I know that K is my metal, so I'm going to draw a line here. This is my metal portion and this is my non-metal portion. Okay, K is potassium. If you ever are confused on the name, look at table S. Here's the symbol. We see that K over here is potassium. Okay, so I know that my first word in this name is going to be potassium, and then I just have to attach this to the non-metal. But here's the issue, right? This non-metal, well, which one are we looking at? Are we looking at the chlorine or are we looking at the oxygen? There's 2 non-metals here. Oh wait, if there's 2 non-metals in the non-metal section of this element or of this compound, this means that it's a polyatomic ion. So there is no name for ClO2, right? It's not an element, it's actually a polyatomic ion. Poly means many, atomic means atom. So it's an ion that's made up of many atoms. So what we have to do here when we don't have a element but a combination of elements as in our non-metal section is we go all the way up here to the selected polyatomic ions and we search for its name. So we see here how ClO2 is chlorite. So this isn't an element, this is actually an ion called chlorite. And even easier, now we just have to attach potassium with this second name. So this is potassium chlorite. So whenever you see, or whenever you're asked to name a compound, it has a metal in it, separate the metal from the non-metal, all right? Then, if there is one singular non-metal, like chlorine here, then attach the potassium, the name for the metal, potassium, with the non-metal ending in IDE. So this is chlorine, but this would be potassium chloride. It'd be ending in IDE. If there's multiple nonmetals in this section here, then you have to look at the polyatomic table, right? And then see that this is chlorite. Number 36 asks us, what is the percent by mass of oxygen in CH3COOH? All right, so whenever we're looking at percent by mass, it's a simple formula. We're going to do the total mass or the total molar mass of this substance divided by the thing we're looking for. All right, so in this case, the element finding or found. All right, so in this case, they're asking us for the percent mass of oxygen. So here in the numerator, we're going to use the mass of what we're finding. So we're finding the percent mass of oxygen. So we're going to have the mass of oxygen divided by the total mass, which they told us was 60 grams per mole. Okay, the gram formula mass is just the total mass for this entire molecule. So we know that this is 60 grams per mole. So we'll put 60 grams per mole in the denominator. Now we need to find the total mass of oxygen, or the species we're finding inside of this compound here. So if we have CH3COOH, I have actually 2 oxygens, okay? So if I look at the mass of oxygen, I can find it over here in the periodic table of elements, all the way up here in the top left corner. That's going to tell me that the mass, or the molar mass of oxygen, is 16 grams per mole. Now, I need to find the total mass of oxygen in this molecule. There's 2 moles of oxygen, there's 2 oxygen atoms here, which means that the total mass of oxygen isn't 16 grams per mole, it's 32 grams per mole. And now I just plug in 32 over 60 into my calculator and I get 0.53, which is equal to 53%. So again, in a nutshell, all we did here was we just found the percent mass. How do you find the percent? Well, it's part over whole. Part over whole. The whole here was the entire mass of this CH3COOH, and the part was the total mass of the oxygen in this molecule, which was 32 grams, because there's 2 of them. Number 37 asks us, given the formula for a compound, how many electrons are shared between the carbon atom and an oxygen atom? So this is a Lewis dot diagram, or a Lewis structure. You know that every single line represents a covalent bond where 2 electrons are shared. All right, so 2 electrons, did not mean to go all the way over here, but you know that 2 electrons are shared between H and C and H right here. So every line represents 2 electrons. That means that if I have 2 lines, that means that there's, well, 2 electrons in this line, 2 electrons in this line, and if we look at this bond as a whole, that means that in total, there's 4 electrons that's being shared, okay? So a single line means 2, 2 lines means 4, and 3 lines means 6 electrons, okay? Number 38 says, which particle model diagram represents the arrangement of particles in a sample of neon at STP? So if we look at the periodic table of elements, neon is Ne, and look at where it is. Well, this is a noble gas, right? This is in a noble gas section. This is a group. It's the 18th group. group number 8 if you want to look at it like that. And essentially what this tells you is that all of these are gases, okay? And that's why they're called noble gases. So at standard temperature and pressure, neon is going to exist as a gas. So we know that choice 3 and choice 4 are automatically out of the running. Why? Because they represent either liquids and solids. Remember that when you put a gas into a container, it's going to take up the space, or a majority of the space of the container. It's not going to be clustered or combined into one another. If you ever see particles that are clustered or bound or locked in with one another, you're either looking at a liquid or you're looking at a solid, which is why choice 1 and 2 are the two answers I'm going to focus on here, because they show neon as a gas, which is what it is at standard temperature and pressure. Now, the difference between choices 2 and 1 is that choice 2 is showing a diatomic neon, right? Neon bound to itself, all right? Remember that there's some sort of diatomic atoms out there, right? What are they? Well, remember the saying Brinkelhoff, right? Bromine exists as a diatomic element. That means that in nature, bromine is often found bound to itself, okay? So bromine, then iodine, also diatomic. Nitrogen diatomic, oxygen or chlorine diatomic, oxygen is also diatomic, hydrogen is diatomic, and fluorine is diatomic. Brinkelhoff, okay, I guess I put the H here, but regardless, Brinclohf, this is exactly what you need to memorize here. All of these are going to exist naturally with two atoms bound to one another. Is neon in this list? No, neon is not in this list. So naturally, which is at standard temperature and pressure, neon will not be bound to another copy of neon because it's not one of the diatomic elements, okay? Moving on to number 39, it says the volume of a 150.0 gram sample of copper at 298 Kelvin and at 101.3 kilopascals is 16.3 cubic centimeters. The mass of the copper sample is expressed to how many significant figures? So we know here that when we're looking at the number of significant figures, we're looking at the mass, which is 150.0. Now, what is a significant figure? Any non-zero number, meaning that any number that's not zero, is automatically significant. So we know that this 1 is significant, this 5 is significant. And then finally, we know that trailing zeros are also significant. So this 0 is also significant. Then, we also know that any decimal with a 0 is significant, right? As long as there's a decimal point here. So this 150, automatically, we should know that that's 3 significant figures. And this 0.0 adds one more significant figure because it's a 0 after a decimal point. Okay, that's what we call a trailing 0, and that's significant whenever you put it after a decimal point. So in this case, we're going to have 4 significant figures. Number 40 asks us which statement describes the energy transfer that occurs when a sample of copper at 100 degrees Celsius is placed in a sample of water at 20 degrees Celsius. So you tell me what's going to happen. Well, if I have this water, which is relatively cold at 20 degrees Celsius, and I put something hot in it, the water will heat up, right? The heat will go and be transferred from this hot block of copper into this water. And as a result, the thermal energy is going to be transferred. Thermal is heat. This copper block has a lot of heat. This water has little to no heat. Heat goes from the hottest thing to the coldest thing. So automatically this heat is going to be absorbed or transferred into the water. When it's transferred into the water is going to absorb that heat. So we're not talking about chemical energy here because chemical energy is stored in bonds, right? If you're dropping this block of metal into the water isn't, degrading the metal or reacting with the metal. What's happening is the heat from the metal, aka the thermal energy, right? Thermal heat, is being transferred from the copper to the water. It's being transferred from the hotter thing to the colder thing. That's how heating works. Number 41 asks which change will cause an open flask filled with water, half filled with water at 295 Kelvin at 1 atmosphere to reach phase equilibrium. So whenever you have equilibrium, the rate of the forward reaction is equal to the rate of the backwards reaction, and as a result, you have no net change. So when we talk about phase equilibrium, that means that phases are changing at the same rate, okay? So what happens here? If I have a flask filled with water, what type of phase changes are happening here? I know that the water is in the liquid form, all right? But what happens when you leave water out for a long time? Doesn't it evaporate? Yeah, it does evaporate, right? And the water level decreases. So why would the water level decrease? Well, that's because the water is evaporating. It's turning from H2O, which is a liquid, into water vapor, which is H2O as a gas, okay? So naturally, if I just let this cup or this container out in the open, what's going to happen is that the water level is going to decrease as just naturally the water is going to evaporate, right, at 295 Kelvin over a very short period of time. Over a very long period of time, that is, unless you heat it up, right? So what I want to happen here is I want to reach phase equilibrium. I want to make sure that the water level actually doesn't change. That means that I want the same amount of H2O that's being evaporated to be condensed back into liquid. So I want two things happening here. Number one, I want the water to be evaporated. And number two, what I want to happen is I want the H2O, that's the water vapor, to be condensed back into H2O liquid. So how can I make sure that there's no net change in my phases? How can I make sure that I don't lose any water? Well, I can seal the flask with a stopper, right? If I leave water out in the open, guess what? It'll evaporate. But, if I put a cap on the water, what does that mean? The gas that that's going to be evaporating, the water vapor that's going to be leaving this container won't have anywhere to go, right? You'll have H2O gas here, but it won't be able to dissolve into the air. So what will happen? Well, it will condense back into the water, or it will accumulate on the side of the bottle. You ever left a bottle of water out in the open, right? Come back the next day, you'll see that there is water or droplets of water all around the plastic, even though the majority of the water is in the bottom of the bottle. Why? Well, because you put a cap on that water bottle, technically you didn't lose any water. The water slowly evaporated, but then it condensed back down into its liquid form, and as a result, there's phase equilibrium, right? So again, you want phase equilibrium, you're going to have to cover the top with a stopper to make sure that no water is escaping, that even if it turns into a gas, it won't be able to dissipate into the surrounding environment, and instead it will recondense down into the mixture here, all right? Number 42 asks us, what is the amount of heat released when 1 mole of NH3 gas is formed from the elements at 101.3 kPa at 298 Kelvin? All right, so we want to find the heat released. So we're looking at H, right? The H in capital H stands for heat, okay? And we're looking at heat released. So we know that we're going to have a negative delta H, right? The change in heat is going to be negative because we're losing heat, we're releasing heat. So if we look at our table here, and we look at table I, heats of reaction at 101.3 kilopascals at 298 Kelvin, this tells us our change in heat in kilojoules, okay? And now we'll look for the formation of NH3. So if something is being formed, that means that it is the result, or that it is a product. So which one of these reactions has NH3 as a product? Oh, well, this one does. N2 plus 3H2 turns into 2NH3, okay? And the heat released by this is negative 91.8 kilojoules, okay? Because it's negative, we know that it's being released, so we know that we're also looking at the correct equation here. So notice here how this is the heat released for 2 moles of NH3. Remember that I want the heat released for 1 mole of NH3. So if I know that 2 moles of NH3 releases negative 91.8 kilojoules of energy, or of heat, how can I find 1 mole? Well, I can just divide both of these sides by 2, and I get that NH3, 1 mole of NH3 is just going to be 91.8 divided by 2. And if we look at that, that's going to equal to choice 1, 45.9. The heat released is proportional to the moles that are involved. So if you have 2 moles and you want to find 1, divide everything by 2. Number 43 asks, given the equation representing a phase change for carbon dioxide, which statement describes the phase change in terms of energy and entropy? So energy is going to tell you whether or not it's released or absorbed, aka whether it's endothermic or exothermic, okay? So energy, if energy is released, it's exothermic, right? If energy is absorbed, it's endothermic. Endo meaning going into, exo meaning going out. Okay, so know the difference. Now, entropy is the amount of disorder, right, or the chaos. So notice here how we're going from solid carbon dioxide into gaseous carbon dioxide. Now, what's more chaotic, a gas or a solid? Well, look back to, this diagram right here. This is the diagram of a solid. Notice here how the particles are all combined together in this rigid structure. Is it ordered? Yeah, it's ordered. Now look at this, which is a gas. This phase diagram shows a gas. Look at how much more disordered it is. It's all over the place. It's not clustered. It's not organized. And guess what? What makes this worse is that these particles are moving freely in these straight lines, and they're causing collisions between themselves and the wall of the container and between themselves, okay? So you need to know that whenever you're changing from a solid to a gas, you're increasing in entropy and you're increasing in disorder because you're going from these rows of organized atoms to these floating, chaotic, colliding atoms, right? So from solid to liquid is an increase in entropy, from liquid to gas is an increase in entropy, and from solid to gas is, again, an increase in entropy. Anytime you're going away from a solid, you're increasing the disorder of the system. So let's take a look at this reaction, right? If I'm adding energy, if energy is a reactant, that means that the system is absorbing energy because I don't see this energy as a product. That means that the energy was incorporated into my system and it has to be endothermic, right? Energy went in. All right. And finally, because we produced a gas, because we produced extra chaos, this has to be entropy increasing. Number 44 asks us which equation represents an oxidation half reaction. Okay. So whenever we're talking about oxidation here, remember oil rig. All right. Oxidation is losing, reduction is gaining. So when oxidation is losing, what is it losing? Well, oxidation is losing electrons. So I guess instead of it being oil, it should be oil, right? Oxidation is losing electrons, reduction is gaining electrons, okay? So if I'm looking at oxidation, I want to see electrons lost. So if I lose electrons, that's a result. I should see the electrons in my products, right? If I have a bromine atom and it loses an electron, then you'll produce a bromine that's more positive because it's lost one of its negative charges in addition to the negative charge that it lost, which is the electron. That's what's contributing the negative charge. So the answer choices that have electrons as a result or as a product are going to be the correct choices here, which eliminates choices 2 and 3. Remember that these guys are gaining electrons. Do I see electrons in the products? No. So where did they go? Well, they went into the system. They got absorbed by the bromine and they got absorbed by the manganese. All right. Now look at choices 1 and 2. We have electrons in the products, which means that electrons must have been lost, right? So now how do I know which one's the correct answer choice? Well, let's look at what happens to the element. Here, bromine is oxidized. It's losing an electron. It's losing its negative charge. If you're losing a negative charge, are you going to be positive as a result or are you going to be negative as a result? Well, think about it. If you drop a toxic friend, are you going to be more happy or are you going to be more negative? You're going to be more happy, right? These electrons are negative. So if you lose something that's negative, you become more positive. But here it's saying that as bromine loses its negative component, it's becoming more negative. That doesn't make sense. You would become more negative if you gained an electron, which is why choice 1 is wrong. If we look at choice 4, manganese loses an electron, right? Where do these electrons come from? Well, they weren't on the reactant side. That means that they were produced. How do you produce an electron? Well, you lose it, okay? And as a result, because this manganese has 2 less negative charges, it becomes Mn2+. It has 2 more positive charges that were being eaten up by these electrons that are now gone. So number 45 asks us which equation represents a redox reaction. Well, this is a half reaction. That's what we were looking at here. We saw something get oxidized. Before a redox reaction to occur, something needs to get reduced in addition to oxidized. So let's see what gets oxidized and reduced here. Which one of these equations tells you or shows something getting reduced and oxidized? So let's look at choice 1. The way that we do this is we have to assign oxidation numbers, all right? And there's just some simple rules that we need to follow here. The first rule is that pure elements have an oxidation of 0. And the second rule is that oxygen has a oxidation of -2 when in a bond, or when bound or bonded to something, okay? So here we have solid carbon. Carbon is a solid at STP, so we know that its oxidation state is 0 for now. Then we see here that we have O2, which is a gas. Remember that oxygen exists as a gas in nature, and it exists as a diatomic element. It's O2. So the oxidation state here also has to be 0. Now we have carbon and oxygen, or CO2, and we see here how this oxygen is bound to a carbon. Now, what do we say? Oxygen has an oxidation state of -2 when it's in a bond. So this oxygen's oxidation state is -2, right? But we have 2 oxygens here. So in total, the oxygens are contributing a oxidation number of -4, right? But we'll just say that the oxygen just has an oxidation state of -2. Now, this oxygen right now is contributing a -4, right? Because each oxygen has a state of -2, and there's 2 of them. But this CO2 has no charge. So how can I balance out a charge of -4? Well, this carbon can actually have a charge of +4. All right, so now let's look at what's happening here now that we've assigned these oxidation states. Remember that the sum of the oxidation states is equal to the overall charge on the molecule. So because CO2 isn't charged, we know that the carbon has to have a charge of +4 to counteract this -2 times 2. So let's see what happens here, okay? So carbon went from a state of 0 to a state of +4. If you became more positive, you must have lost something that was negative. So oxidation is losing, so carbon got oxidized. And if we look at oxygen here, it went from 0 to -2. It got more negative. So that means that oxygen here got reduced. And guess what? Because I have oxidation and reduction happening, this must be the only redox reaction here. Now, this is a lot of work. That's because I'm explaining it step by step. All you need to know here is that pure elements that just occur naturally will have an oxidation of 0. All right, oxygen will always have an oxidation state of -2. Assign these numbers to each one of these choices and literally see whether or not there's a change in the oxidation states or not, right? And then also see whether or not if something is oxidized, something is reduced, right? Make sure that these two happen at the same time. If you only say one thing is being oxidized and nothing else is reduced, or the other way around, guess what? It's not a redox reaction. Red, ox, reduction, oxidation reaction. Two things need to happen at once. Number 46 says, based on table J, which metals will react spontaneously with Fe2 plus ions? So only metals that have a higher reactivity will react. That should make sense, right? Metals that are more excited than Fe2 plus will react with Fe2 plus. So if we look at table J, here we have Fe right here. And then if we look at the metals here, silver, gold, and magnesium, silver is right here, gold is right here, and copper is right here. These are all less excited or less active than the iron, so they won't react with the iron. What will react with the iron is this magnesium up here. The magnesium is more active, and as a result, it has more energy to go ahead and react with this Fe, which means that the magnesium will be the metal that will react, okay? Whenever you're trying to see whether something will react or not, see whether what it's reacting with has a higher energy. If it does have a higher energy, the reaction will undergo. Number 47 says, based on table F, a saturated solution of which compound is the best conductor of electricity? So if you want something to conduct electricity, you want the solution to have a lot of ions. Okay, ions are positively and negatively charged particles, right, or atoms, and that's good for electricity because you want electricity to move from the positive end to the minus end. So the more ions you have in your solution, the greater a conductor of electricity it will be. So essentially what we're looking for is, well, how do you create an ion? Well, you create an ion by dissolving something in water. So for example, CaCO3, well, that's Ca2 plus and CO3 2 minus. These are ions because they're charged. But CaCO3, we need to see whether or not it will actually dissolve in water or not to produce those ions. So to see whether or not something dissolves in water, we need to go into the solubility guidelines, okay? So let's check CaCO3 out. So calcium carbonate, right? Sorry, calcium, I think it's carbonate. CO3, yeah, calcium carbonate. So ions that will form soluble compounds. If something is soluble, it will dissolve, okay? So, oh, wait. Why waste our time reading this when I see that carbonate is an ion that will form an insoluble compound? Guess what? Insoluble means having very low solubility in H2O. What that means is it will not dissolve. So guess what? Calcium carbonate is combined, well, has carbonate in it, and the exception is when combined with group 1 ions. Calcium is a group 2 ion, so as a result, it's insoluble. It will not dissolve. If you're not going to dissolve, then there's no way for the Ca to split into Ca2 plus and CO2 minus. So because this isn't producing any ions, it will be a poor conductor of electricity because there's no ions being produced. Let's look at BaSO4 again. Well, barium, or SO4, right here. Sulfates are going to form soluble compounds except when combined with Ba2 plus. Oh man, BaSO4 is actually insoluble. It's not going to be dissolved because this SO4 has an exception. It's not going to be soluble when it's combined with barium, which it unfortunately has, okay? So now let's look at MgOH2, all right? So we see that hydroxides are insoluble except when they're combined with group 1 ions, calcium, barium, strontium, or ammonium. Is magnesium any one of those? No, it's not. So it doesn't meet the exception, and as a result, it doesn't dissolve. So that leaves us with choice 3 is the right answer. Choice 4 is the right answer. Choice 3 does not dissolve. NaNO3. Let's look at the rules here. Ions that form soluble compounds. Group 1 ions. Oh, Na+. Anything with Na inside of it will dissolve. No exceptions, okay? So NaNO3 will be the only one that's actually soluble in water. It'll be the only one that produces ions when dissolved, and thus it'll be the best carrier of electricity. Number 48 asks, given the equation representing a system at equilibrium, according to one acid-base theory, what happens? Well, you know that acids, that they donate H plus, or they donate their protons, and you know that bases have to accept H pluses. So let's look at what happens here. We started with HSO3 minus plus H2O, and what did we end up with? Well, we end up with SO3 2 minus. Wait. How did we get this SO3 2 minus? Well, what's the difference? Well, I see that it has SO3 in it, and this one has SO3 in it. Oh, but the difference is that this one doesn't have its hydrogen anymore. And it's also more negative. Why is that? Oh, well, it probably gave up its hydrogen, right? It gave up its positively charged hydrogen, which is what we call a proton, okay? So this SO3 2 minus is missing a proton. Why? Because this HSO3 is an acid. HSO3 has to act as an acid because it's an H plus donor, and it's donating or giving this away to the H2O, because now you have H3O positive, right, or H3O plus. Where did it get the extra H from? Well, it had to have been donated by the HSO4. The proton was gained from the HSO3 because it donated it to the H2O to form H3O, or hydronium. So number 49 asks us, what is the pH of an aqueous solution with a hydronium ion concentration that's 1,000 times greater than an aqueous solution with a pH value of 5.0? So let's look at what the pH scale does. The pH scale pretty much relates the amount or the concentration of hydronium, which is H3O, inside of an environment, okay? The pH scale ranges from 1 all the way to 14, okay, with 7 being a neutral pH. So because the concentration of the hydronium is 1,000 times greater, that means that that new concentration is more acidic. And the more acidic you are, the lower your pH is. So this is acidic pH, this is a basic pH. So right now, that solution that we're looking at here has a pH of 5. Every level on the pH scale represents a 10-fold increase. So the difference between a pH level of 5 and a pH level of 4 is that a pH level of 4 is 10 times more acidic, or it has 10 times more hydronium. All right, what's the difference between a pH level of 4 and 3? Well, again, pH level of 4 has 10 times more hydronium. All right, what's the difference between a pH level of 3 and a pH level of 2? Well, a pH level of 2 has, again, 10 times more hydronium than a pH level of 3. And look what I just did here. What's 10 times 10 times 10? Well, that's 1,000. So technically, the pH level of 2 has 1,000 times more hydronium than a pH level of 5. Oh, isn't that what we're talking about here? Yeah, it is, right? A hydronium ion concentration that is 1,000 times greater than something with a pH of 5 is just 3 pH units down, which is choice 2. The other way you could have done this was you could have calculated the pH change here. If you have 1,000 times greater concentration of hydronium, take the negative log of 1,000, because that's what pH is equal to. pH is equal to the negative log of the concentration of hydronium. The negative log of 1,000 is going to give you 3. So you know that because your concentration is 1,000 times greater, your pH is 3 levels lower. I would recommend drawing the table out like this, but if you want to just do the calculation using negative log, you can. Number 50 asks us, which energy source is paired with the risk associated to its usage? All right. The only issue here is that nuclear fission produces nuclear or radioactive waste. That's the only health risk, or the only risk that we have, right? Even though nuclear power provides extremely clean energy and it's super safe, the issue is once we use up our nuclear fuel, we just have a bunch of radioactive waste, okay? Voltaic cells are batteries. Batteries do not produce radioactive waste, and if you're producing stable isotopes, that's not a risk, that's a benefit. Same thing with 1. If you're producing stable isotopes, that's a benefit, not a risk. So which one produces nuclear waste or radioactive waste? Your regular AAA battery or a nuclear power reactor? Well, obviously a nuclear power reactor. So that's the end of this video. If you have any questions, please feel free to let me know in the comments below. If you want to keep reviewing this test, I've already uploaded that video. Just check it out in the description. I've labeled literally which video is for which part. Hope you like this video, and I hope you have a nice day.